and actually, I'm not sure.
Busy. Channel. No, it's
Oh, yes. Okay. No, no. So today
I want to start out before the German students join us by just doing a little bit of Blender and showing you some of the things that you can do with it. In particular, right now, one of the prompts that we have for the hackathon is the fact that we want to have the robot, a wheeled robot with a camera, drive around and recognize these different cards. Right? That would be one of the issues that we have. And this morning, we tried and used large language models, and they weren't so successful in detecting the cards the way that we wanted them to. So now we can think about different ways of implementing the actual perception, the card detection. And I think convolutional neural networks, followed with max pool layers, 3 levels of this, followed by MLP, should work quite well in solving this particular problem. But if we want to do that, then what's the main issue? If we want to follow this particular route, as opposed to, for example, saying, I'm going to look for orb features on the card, I'm going to try and detect edges and lines and blotches on the card. If I want to use a neural network, then one of the issues is the biggest issue. Which is kind of true for all of modern AI. Your biggest hurdle is going to be to get good quality training data. If you have good quality training data, your machine learning system is going to work. If you don't have good quality training data, then it's like playing Russian roulette. It probably will not be very successful. If you have poor data, then all hope is lost. It will definitely not work. So how do we get training data? So sure, if somebody else wants to do our magic trick, the one I just came up with last week, and already collected 1 million pictures with that, then sure, we would be golden, right? But chances of this happening are extremely low, right? And even if you look for online sources of playing card images, then they are, but most of them are going to be like head on, like 90 degrees to the plane of view, to your camera plane. Which means that that's not the view that our robot is going to get, right? Because we're going to drive around, so we'll have to look at the card from a view that's distorted by perspective distortion. And so, first of all, what actually happens when we look with the real card, with the real camera at an object like the cube here, for example. Then last class we talked about homogeneous coordinates and then differential drive. Yes, but I mean when we talk about homogeneous coordinates, what did we use them for? No, that's the one thing we didn't use them. If I have some kind of figure in vector format, right, and I use homogeneous coordinates, so x, y, z, 1. Now I have some transformation matrix, A, and then new set of points. Then what can I do with this matrix A? What can I model? Right. What kind of transformation? What transformation do we talk about? Rotation, right? Translation, yeah. Anything else? Scaling, yes. And skewing, correct. So it's those four things that we can do, right? And because of the fact that we have it in matrix form, that means I can keep multiplying to the left. So what I can actually model is the compound of this. So I can do a rotation by 10 degrees followed by a translation, followed by a rotation by 12 degrees, followed by a translation, followed by a skew, followed by a scale, followed by another scale. Then I just can keep going on and on and on. And so this kind of power set of this is what I can generate. So the one thing that we cannot do is this effect, right? Which is actually the perspective distortion. Right? And what happens when we're dealing with the perspective distortion? What happens if David holds the pen up here, right? And now go back? What happens to the pen for my visual field? It becomes smaller, right? So things that are further away become smaller. And that's a perspective distortion. So now if I want to model a camera system, I can move the camera, right? I can rotate the camera, and here, this would be a 4x4 matrix. I could scale the camera, which would model if we zoom the camera. And skewing, there's no camera effect that does skewing. There's nothing that we can do. And zoom is not if you zoom into the image plane, but if you actually have a physical lens that can move. So then we could model that as well. So the perspective distortion is not something that we have discussed so far. Now, when you actually look up homogeneous coordinates on the internet or in a textbook, then they usually don't look like this. But they make perspective, they make homogeneous coordinates are usually represented in this form. AX, AY, AZ, and K. So if K is 1, then we get this one. Right? Because this is 1 times X, 1 times Y, 1 times Z. But now the mapping from real world coordinates to homogeneous coordinates is not unique anymore. Because these all of these points would correspond to the coordinates 2, 0, 1. These homogeneous coordinates, minus 2 divided by minus 1 is 2, 0 divided by minus 1 is 0, minus 1 divided by minus 1 is 1. 4 divided by 2 is 2, 0 divided by 2 is 0, 2 divided by 2 is 1. So all of these map to the same 3D coordinates there. So mathematicians, they have some other reason for preferring this kind of generalized version of homogeneous coordinates with an arbitrary k as opposed to just having a 1 here. So far, we only needed the 1 here, really. Right? That was the only reason why we added the 1, was in order to be able to do translation. Now we have a generalization here. This generalization has mathematically some, the mathematicians like it because for them now they can project points at infinity that are infinitely far away. If you make 0, k equals 0 here, then this is actually not defined because you would have to calculate kx divided by k, which would be a division by 0, but you can then project it further. And this thing is like something that is important for higher level mathematics, but for practical purposes, I'm not really that excited about this, right? However, the cool thing about this generalized form of homogeneous coordinates is that it actually allows us to model the perspective distortion. So that makes it extremely useful for our applications in robotics. So now, how does that work? In order to make that work, we need to look at how the projective, how the camera actually looks. Now, the model that we're going to use for the camera is a very simple one. It's called the pinhole camera model. So if I have a stylized view of my camera, then there is an image plane, there's a sensor, right? Our CMOS sensor, CCD sensor, whatever we have, depending on the internal structure of the camera, or in the old days it would have been some analog film that you have in the camera that will be exposed to the light that you would need to develop afterwards. So here's our sensor. And then at one point, ahead of the sensor is a single mathematical point, which means it's infinitely small, the tiny, tiny point, and that's the only way that light can reach the sensor. So this whole thing is enclosed. And this will be our camera. Now we get a response on the sensor by some light from some object. Here's a tree. Some part of that tree, there's some light shining on it. That gets reflected in arbitrary cone, and then part of that light is going to go through our pinhole and hit the sensor. Then we can measure the number of electrons that are captured, the number of photons that hit there, which knock out the electrons, which is how we measure the voltage at this particular cell. And that's how the image is done. We do this for many, many pixels, many, many rays, and then we get the picture. So now let's put this onto a coordinate system. We'll make that our distance from the camera, so we'll call that Z. We align the camera. Actually, depends on if you have done this before using Blender or game engines, if you've programmed in Godot or Unity or something like that, then this is always quite exciting times, because not all the game engines agree on which one is the axis away from your camera. OpenGL assumed that the axis for the camera was Z. That was your depth from the camera. And some of the graphic standards use Y. And then there's a difference about Y up or not up. So we just call it the Z axis here. But I could have picked the X and Y as well. Some X, nobody uses X. Some people use Y. Now, for the camera, this distance here from the actual sensor to the pinhole, that's called your focal length, which is either f or lambda. Those are the common variables for specifying that this is the focal length of the camera. And now what we detect is an image, right? And in this case, usually it's a plane. It's a 2D sensor, but I only look at it from the side, so we only care about the x-axis. So this is the position that my sensor reads. Let's call that U. And this would be the real-world coordinate that I'm measuring x. So x maps to U, y maps to v usually when you deal with the camera. And okay, now this part here, this ray here that goes through the optic, through the pinhole, that is 90 degrees to the image sensor. That ray is called the optical axis. And it would be like the 0 point of your image. Now, given this kind of camera setup, then what can I actually do? Well, first of all, we can see how the same object, if I move it away, will become smaller. Right? Because this is the pen at 1 meter. This is the pen at 2 meters. then the image of the pen is going to become smaller. Because now the light is going to go from here through the pinhole, so it's going to hit somewhere close to it. So that's why, as things move away from you, they will become smaller. And that's the same for the human eye. Very, very close to what the human eye is. So that's why the same thing happens for us when things move away. So now what we want to know is, what I can know is, if I've given x here, if I've given x and I'm given z, then what can I calculate? Oh, camera. People are just growing? Or how does this trick work? That's because your eyes can't really determine this. So by putting this new checkerboard pattern, this is not really a checkerboard pattern, 90 degrees to where you are, but actually the distance is like this. So the guy walks from far away to close, which is why he gets bigger. Right? And there, you cannot tell the distance there. Right? Nobody can. But this floor here is made in such a way that it looks as if that wall is 90 degrees and they walk left to right. But actually they don't walk left to right, they walk front to back and a little bit left to right. And that's why how that works. So if you see something in the image, you cannot tell the distance. Unless you have some additional information. So how do humans solve the distance problem? Binocular vision, stereo vision. Right? So we have two eyes. I can look at the parallax. I can see how much things are jumping. For things that are like up to (1.50 m) or something, that's what we use. If you need to use a needle and you thread a thread through a needle hole, the eye of a needle, then that's what your brain uses in order to be able to do that. It needs to be very fine accurate. Most of the time, people don't actually use stereo vision that much. For the door, for example, the parallax shift is already quite small. Anything further away, a tree in the distance, we don't measure the distance to that tree using parallax for stereo vision. How do we measure the distance to the tree? By having a model of how tall trees are usually. Right? So if there is a car, you estimate the distance to whatever is beside it by thinking, okay, how big a normal car is. And that's how you can fool people. If I make a really tiny car, then I can tell you that, oh, this little doll that's beside is enormous because, see, the car is tiny again. So a lot of the things that we do are based on, a lot of the perception that we do are based on world models. In robot soccer, we need to measure the position of the ball relative to the robot so we can kick it. If we want to do that, then we have some additional pieces of information, because up to now, most of the soccer play for robots is with the ball on the ground. So I know that the z coordinate of the ball is 0, or the bottom of the ball must be z equals to 0 if it's on the ground. And then I can also measure the distance. That works. You can also use specific features. So if I have a navigation path and I'm looking for computers, for example, and I can of course assume that the computer is on the floor, or I can use the width of the ball or the width of the computer, because I know what that number needs to be, right? So then I can also figure out what the distance is to the computer. But we do need to have some additional piece of information. Now, as far as the data is concerned, X, Y, Z, the real-world coordinates of the object, and U and V, they change, right? If I have X, Y, Z, and then I take a step here, all the coordinates are different. However, this focal length That one is actually constant. That doesn't change. Once you build the camera, the focal length will remain the same, unless you have a mechanical zoom camera. If you just have like electronic zoom, like you just zoom into the image and it scales it up, then that won't affect it either. But if you actually have a camera that physically moves the lens, it will move this position further forward or back. But most webcams don't have zoom, right? So a webcam, for example, would have one focal length and it'll stay the same after it's been built. So now what does this function look like?
Hello?
Yes, Jackie. Um, I make you presenter. Huh? Okay. Ah, yeah. Perfect. So, Jackie, you should be able to share your screen now. And for
It should be in my camera.
yeah, well, we just see your camera view, not the desktop or whatever. For next time, I send you an email with the code to start the video conference system. Yeah, perfect. Racetrack diff and so on. So we won't
Okay, good.
have
Then
all
let
students
me share the other screen first.
Yeah. So we won't have the students to fill the video conference. Yeah, well, in principle, yes. Practical, maybe no. Because we have 80 seats in this lecture.
Morning, Mr. Jan.
And yeah, that's perfect. So we do it by end of the month, we will decide. However, this will need to happen yeah, but we could do the other one called next semester.
This one?
You know, if you have any issue, please report.
What's the file type? HTML? No.
I'm the lecturer. I was already, I received.
Save the
one.
image.
So I cannot take 150. So that's why I said, well, we should be able to get around 80.
Oh. Yeah, you can do that.
There is a chance because a lot of them show up at the first week, and then they drop out. So that's your opportunity. Jackie, just a short announcement from my side.
Say again, what?
There is a short announcement on my side, so if you just
Okay, go ahead.
Minutes,
Yep.
we can. So there is an issue with this class. Huh? We had about 150 registrations. And because I was one, I'm not allowed to take that many students for a couple of reasons. Among others, it's for fire protection. You will not be able to access this room in case there's a fire, if it would be 150. So I need to limit the number. I agreed to limit to 80 because this room holds about 70 and typically there's about 10 of you who feel sick or have some other complications. So it's limited to 80. In the first week, 80 of you or your fellow students submitted the assignments. So that's why these 80 are enrolled. Typically, some of these, about 70, couldn't be enrolled. They are just on the waiting list. Typically, there's a number of these 80s to disappear. And that will be the option for the others to get a place in this lecture. Yeah, and we will decide by the end of the month. So the issue is, by the end of the month, I will look into the submission of the assignments. If you didn't submit, you're out. If you submitted everything and some of the 80s who were enrolled didn't submit, they are out and you will take their seat. That's the rule. Some of you may have an issue because of the limited number of lectures in English. So what you could do if you can't get a seat, but you see there's a lot of space now, and we're supposed to have been started 5 minutes ago. But if you don't get a seat, if you need this lecture for some reasons, you want to graduate, you need it in English or something like that, you can, for the digitization students, you can complain to the head of the examination board. Well, maybe it's the same for the computer science people. The digitization people, then I have to deal with this. So you complain about this class not having sufficiently many places. In my class, and then I need to deal with this as head of the examination board. But you need to send an official mail. But please wait until, it should be after Easter, something like 6th, 7th, 13th of April, probably. because the Easter Monday is a holiday, no? So there's no lecture on that day. Okay, today we should have two parts. One part is Professor Borges. The other part will be my part, which we will be talking about the chapter of the book, which I still will be read. And we will talk about some activities you need to start to prepare for the remainder of the class. Okay, Jackie, the floor is yours.
Okay, good. And thanks for joining the class again. Today, I just want to talk a little bit about Blender. The reason why we're interested in Blender for this particular hackathon and project is that to do the vision processing, I would like to use a CNN, a deep learning network, in order to detect the cards on the playing field from the robot. And in order to be able to do that, in order to train a neural network like that, we need to have some sample training data, right? We need to have some, and in fact, not just some, we need to have a huge amount of training data. Now, the usual way of doing that and getting the training data would be to put cards onto the floor and then take pictures of him, drive the robot around, and record videos, and then extract images, various types of images. That's a lot of work. Then you need to find the ground truth of the card, right? Because you need to actually know the position of the card and the orientation. And that is quite troublesome. Now, I know some professors, especially the computer vision professors, if you want to do a master's thesis with them, the first thing you do is for 2 months, you just sit there and label images, right? They say unless you label 2,000 or 5,000 images, they won't accept you as master's student. And I can see the appeal of that. I know why they need to do that. I just think it's a huge waste of time and not something that we really want to do. So we'll use synthetic data, and one way of getting actually high quality synthetic data is just using a computer graphic package like Blender to actually generate it. So today I just want to give a little introduction to Blender. It is primarily a computer graphic package. It is extremely powerful. In fact, the winner of last year's animation Oscar. So Oscars just happened yesterday, I believe. A huge thing big in Hollywood. The animation was actually done for Blender for the winner 2025, which is called Flow. So here's an interview with them, and the way that they made this Oscar-winning movie is quite interesting, of course. They are a lot more skilled than I am, and also it's a Hollywood movie, so they require a lot more accuracy than we need for our training data. So for the Blender interface, you can download it from blender.org. And install it. It's open source, so it's free. There's no legal issues. And Once you start it up, you'll get a screen similar to this. You can rotate your camera or your object by pressing the middle mouse button. You can also use these gizmos here by clicking on different views, top view, for example, bottom view. There's a camera built in to the default scene, so you can have a view from the camera. And here we just have a cube. In order to move things around, G to pack things up, move it around. G, Y to constrain it to one axis. GX will move it in the x-axis. S to scale. And R to rotate things around. Now for our problem, where we have a ground floor and we just want to show a card, this is actually easier. We can take an object X to delete it, and then I want to add a image, so A to add, or add object add. And then here I want to add an image as a mesh plane. And then I downloaded one picture already. So here we have a jack of spades. So here's our card. That's the back of the card. This is the front of the card. Jack of spades. You can do all of the cards that you would like to do. And this but I want it flat on the ground, so I can rotate it around the y-axis by -90 degrees. Then this is what I can see from my camera. Now the camera is a little bit far away to be able to recognize that possibly. And then we can add, I can change the Z coordinate here. Move it 1 millimeter up. Then I can add another mesh for the plane. And here's now my plane, and I want to have that plane green. So then I have to deal with materials. I need to make a new material. It's a solid green, not quite so bright. Now just look at the top, find the camera, and camera navigation. I can move the camera a little bit closer, and then bring it down a little bit. You can also limit it to the XY plane only by hitting Shift Z. Now I can move the card around wherever I want it to be. That also works. And then you can export, you can render this using Light. And then you have a picture that you can pretend came from your robot. Now this is obviously doesn't have as much noise in it. If you wanted to, you could add noise. There's always to make it very realistic, but it's a start where you can generate thousands of card images, because the one nice thing about Blender is that you can also use scripting, so you can program it in Python. Now I made the window too small. So here's scripting. And for example, that how you import it. Oh, what happened now? So for example, I could take the card and find it. So there's also a Replit that you can use. Let me just save it. And there's various ways to define the rotation in the Python script. One is Euler angles, axis angles, or quaternions. In this case, it's very simple. I just want to rotate around z coordinate. So, Euler is using 3 angles. Take it. Now the Z angle has changed, so I thought there was a way to rotate it. But scale. I thought it was Z. And what did we have here? Rotation radius.
It's called here our radians. I have to give the angle in radians. So 0, 0, 45. Convert 45 degrees into 30 degrees. 35 degrees into radians. Just set it. So now we can change the card around and make it look cooler with the light. So that allows you to generate lots and lots of. I can also make it rotate in 10-degree steps. Rotation whether 0, 2. Z axis. And here. So this should rotate it by 10 degrees relative. So you can see how things rotate around. You can save, you can render the image and then save it. So we look at the view from the camera. And we can rotate that around. I can translate the card backwards and forwards a little bit. Let's see. Here, just do it for one. Get the position. Location. So then let's say I want to take the card, bring it kind of in the center of my view, and rotate it 0 degrees. That's my starting position. And then pi, so I generate an angle, I generate a distance, which is random dot random, multiplied by 1.7 meters. There. 1 meter. Then the new x position would be x plus mass multiplied by the distance, and this would be y plus mass plus line angle multiplied by the distance. And then I want to rotate the thing, so the new Euler 2 then I just rotate the card by 2 times mass of pi, and then card dot rotation is equal to x and y and z. Card dot rotation Euler is equal to I think I can just do this. This would be theta n. And now my card flips around the table. can render it. And that allows you to generate thousands of training images. Also, of course, you can save the render. There's one trick, yes. This double slash for file name in Blender gives you the current position in the output path. So now here I want to change it. So this would be the name of the card is JS. If you have multiple cards, you can render those. Then I want to give it the X and Y coordinate and the orientation. So PNG. And then we render the scene and save it. So here we save it as a PNG file in RGBA format, 8 bits per channel, and
Yesterday.
Now Now here I save the data in the file name, which is problematic. It usually works, but if you have a number 1.00034971215 so on, then it will write that out in whatever the default function is. So probably would be worthwhile to simplify that x, y, x, xs, ys, z, theta, z is equal to round xn equal to convert that to strings first. And then I also want those replace the dots because they sometimes cause problems in the file name by what are the simple functions? I just did, replace it with underscore. Let me just try that. Round 1.234 2. Bring up this. Replace the dot with the underscore. And when I save it, make it a negative sign doesn't work either. Then I make it. Okay, let's see. String was rows. That's correct. Now put here. Put here. Okay, So that actually ran now, and let me check where I saved. Oh, rock climbing rope. That would be, oh, magic card trick. Oh,
Ja, einfach das.
Hearts of Lamb.
Das wir dürfen Aufgaben, wir dürfen jede Programmiersprache nutzen. Nur kein Excel. Einmal das ist einfach. Das ist nicht gut. Da manche freut sich. Der macht den Bleiben. Und der ist es. Ja, nur. Was ja ruhig. Du weißt ja auch, du hast ja keine Sprache. Das bin ja eben noch nie schon.
And here now is the data. Like it's the jack of spade at x location 0.03, y location negative 0.3, and 106 degrees. Now, instead of running through the loop one time, I can run through 1,000 times. I get 1,000 different cards. And their positions. Some of them cropped, some of them not cropped. You can add more noise later on. So that's quite useful. It allows you to, it's quite a powerful program that allows you to generate lots and lots of training data for your vision algorithm. Okay, so any questions so far? Okay, good. Then I would like to have you work on a small project here based on our racetrack differential drive robot. Which it is here. I would like
Scheiße, ich weiß nicht, was das ist. Wir kommen da jetzt drauf. Discord. Habe ich das Utility Minecraft? Nee, aber auch echt mal. Zeigen wir mal die Tafel. schönes Schreiben muss. Das funktioniert.
Perfect. I think we kind of finished them off. I don't know if there's any concentration left for my part, but thanks a lot. See you next week. Okay. I've seen many of you taking some breaks in between, so we don't need a real break, or do we? Okay, so let's do 10 minutes, then we meet again. So 10 minutes break, yeah?